This video will cover an extension of the idea of row reduction to computing inverse matrices. So we've talked about matrices being invertible and what that means. Basically the fact that I'm trying to find a separate matrix that when I multiply it by what I start with, I get the identity back. But how do we figure this out? Well, we can think about figuring this out in terms of what matrix multiplication actually looks like. So if I have a matrix A, and I take my matrix B, and let me break it down and sort of write out what the matrix is going to look like, assuming that we have a 3x3 matrix here. How do I get to the first column of the answer? Well, if I want to get at the first column here, I'm always taking rows of A times columns of B to put me into a spot of the resulting matrix. So everything for that first column actually comes from the first column of B, because it'll be multiplying row 1 of A times column 1 of B to put me in the first slot, row 2 of A times column 1 of B to put me in the second slot, and row 3 of A times column 1 of B to put in the third slot of that first column of the output. So if I want A times B in terms of matrices to equal the identity, then I need the first column of B to satisfy A times that vector equals 1, 0, 0. And the same argument will say that the second column should satisfy A times that vector equals 0, 1, 0. And the third column should be 0, 0, 1. Now all of these are just solving a system of equations, which we could do by row reduction. But the same process will work for all of these setups. We'll just get a different right-hand side. What we can do is we can actually solve all of these problems at once to get to the answer. So the idea is to build a bigger augmented matrix. So we'll have A on this side, and on the other side we'll have all of these columns all in a row. So we'll actually just put the entire identity matrix on the other side. And then we'll row reduce until the part on the left becomes the identity matrix. It must become the identity matrix under row reduction to get to reduced row echelon form, because it's invertible. We know that's going to work. So row reduce until we get to an identity on this side, and it turns out whatever shows up on the other side is going to be the inverse matrix, because the columns of that will be the columns of B that we need, so as a whole, that unit is the inverse matrix. Let's take an example and see what that might look like. I want to find the inverse of this matrix here. So what am I going to do? Well, I'm going to build that matrix and build an augmented matrix that tacks on an entire 3x3 identity matrix to the right-hand side. And now I'm going to row reduce to get this left chunk to be the identity matrix, and whatever's on the right will be the inverse. So let's get rid of the 2 and the 1 down here because they are below this pivot 1 up top. That's going to give me the first row staying the same. Subtracting 2 copies of row 1 from row 2. Adding 1 copy of row 1 to row 3. You'll notice the steps on this side indicate exactly what you're doing to the matrix. Now I can multiply row 2 by a -1 to get to a 1 in that spot. And then I can add 1 copy of row 2 to row 3 to get rid of that -1 at the bottom of column 2. The first 2 rows here stay the same. Adding, adding, and then finally to get to a 1 in this last spot here, I can divide the entire third row by a -14. And now, since we need to get to reduced row echelon form, or the identity matrix on the left, we need to back solve up and get rid of these numbers that are above the pivot 1s. So I can now use the last row, this 1, to cancel out this 9 and this 4. So now the bottom row stays the same. I can add 9 copies of row 3 up to row 2. Put a 0 here. I'm adding, so I'm getting 2 and then minus a 27 over 14. which is going to put a 1 over 14 in that slot. -1 plus 9 over 14 gets me a -5 over 14. And that just adds a -9 over 14 to that spot. And then to the first row, I can add 4 copies of row 3 to cancel out that -4. So I'll get 1 and 3 that stay there. I get a 0 in that spot. 1 plus 4 times 3 is 12. Gets me a 2 over 14. And the last 2 are zeros. So a 4 over 14 and a -4 over 14. It makes sense to leave these here in terms of denominator of 14 because that's going to cancel out with the next step that I have to do, which is now subtracting 3 copies of row 2 from row 1 to get rid of this 3 that is here. So the bottom 2 rows will stay the same. The first row here now becomes a 1, 0, and a 0. I'm now doing 2 over 14 minus 3 times 1 over 14. It's a -1 over 14. 4 over 14 minus 3 times -5 over 14. So that's 4 plus 15, or 19 over 14. And -4 minus 3 times 9 is -4 plus a 27 is a 23 over 14. And so that tells us then that the inverse of this matrix is exactly this. -1 over 14, 19 over 14, 23 over 14, 1 over 14, -5 over 14, -9 over 14, -3 over 14, 1 over 14, -1 over 14. Now, yes, long, tedious, complicated, but a fairly straightforward algorithmic process to compute the inverse. And it allows us to then compute the inverse of these matrices just using row reduction. So that's the idea of how row reduction can be used to find inverses, taking an invertible matrix and using row reduction on it, paired with an entire identity matrix, to then compute the inverse of that matrix.